I'll present here our solution for detecting breast cancer through thermal imaging. It's a joint effort between LABZ.ai and ThermaScan. Here is the outline of my talk. First, I will briefly introduce what thermal imaging is and how it can be used in healthcare. Then I'll talk about breast cancer, the problems with the current screening protocols, and then go on with the introduction of our method for using thermal imaging for detecting breast cancer. So what is thermal imaging? So basically, the infrared detector in the thermal camera detects the infrared radiation, and then you can transform these intensities, the detected intensities, into temperatures using the environmental parameters and the parameters of the object that emits that radiation, like the emissivity. And then you can visualize these temperatures in a way you want. So thermal technology developed quite fast. The plot shows the thermal resolution and the size of these detectors with the time, and we see that compared to 1960s, where the first infrared camera was introduced, the size goes down and the resolution goes up. And currently, again, compared to 1960s, where we had this huge infrared camera, now we are down to basically less than 1 gram for the detector, and the size is smaller than the width of a pencil. The reduction in size and the increase in thermal resolution enables to put these detectors in various hardwares like smartphones. In 2020, so FLIR 1 Pro introduced its attachment. So basically, it's an attachment that you can put on your Android. And then take the thermal cameras. Actually, this was the first thing that we used when we're collecting our data. Then CAT company, you know, this construction company, introduced the CAT S62 Pro, which basically has the same infrared detector as in FLIR 1 Pro, but it's embedded in the smartphone directly. And this is easier to use because the attachment, the battery life was quite short, like half an hour, 1 hour. And it was, I mean, practically speaking, it was harder to use for the doctor to take the pictures. So thermal imaging in healthcare has a quite long history, actually. And the first usage of thermal technology backs to the days of Hippocrates, where wet mud was used on the skin, and then they would observe like the regions where this mud was drying the fastest, and this would indicate a tumor swelling, for example. But for quite a long time, for 2 millennia, the measurement of temperature remained a subjective skill, until Galileo Galilei made his famous thermoscope in the 16th century. Fast forward another 400 years, and we can measure temperature with a smartphone. So breast cancer screening. Breast cancer is a huge problem. It's the most common cancer among women globally. In 2020, more than 2 million women diagnosed with breast cancer, and 700,000 died. The deaths are mostly associated with late detection, especially in developing countries where there is a lack to screening programs and accessibility issues. So the current status of breast cancer screening is mammography, ultrasound, MRI. But this is not likely that low and middle income countries can afford these huge screening programs. For example, in EU, they have the program until after some age, women go to regular screenings, like 1 year, 2 years with the 2-year period. And basically, for every 1,000 mammogram images, they detect 5-6 cancers. Yeah? But even with the good screening program, there is still the incidence of so-called interval cancers, where the cancer develops in between these two regular screening sessions. For example, in England, 6,000 interval cancers each year develop, and 80% develop because the cancer actually developed in between these screenings, and 20% were basically misdetected. I mean, they were there during the previous screen, but they were not detected. So why cancer can be detected with thermal technology? What is the idea? Why we are here? So the reason is that the cancer cells are metabolically more active, and because of this, the cancer tissues tend to be warmer than the normal tissues. Also, for the cancer to grow, it needs to basically create new veins in order to keep the supply coming. And these two processes, the metabolically activity and the angiogenesis, this formation of new blood vessels, is the main reasons why we can detect breast cancer with thermal imaging. Also, there is inflammation associated with the cancer, which also helps in detecting. So we started the project in 2020. We partner with Erebuni Medical Center Breast Unit. We have collected 3,000 plus, screened 3,000 plus patients so far. And the screening consists of taking 3 thermal images from the frontal view, left and right oblique views. So we have 9,000 plus images. The images are taken before the standard screening, mammogram and ultrasound. And there is some protocol to be followed. For example, the patient needs to sit still for 10 minutes naked, so that the body becomes in thermal equilibrium with the environment. Yeah? The idea is that, there can be warm regions on the breast, but the normal healthy tissue comes to thermal equilibrium with the environment quite fast. 10 minutes is usually enough, 10-15 minutes. But the cancer tissue doesn't come to thermal equilibrium, and you can see the hotspots. Once we take the thermal images, then the patient goes to normal screening, which consists of usually mammography, or if the result is not clear, ultrasound. And then if the risk is high, patient usually is advised to go for a biopsy, and in the cases where the patient went to biopsy, we also have the data. So how we define our ground truth? So the usual scale for mammography, ultrasound, and MRI is this BI-RADS scaling, breast imaging reporting and data system, which is a number between 0 to 6. So 0 means it was not conclusive, there is a problem, no data. In these cases, we discard the patient from the study. 1 means definitely negative, there is nothing, no risk. 2 means we can see something, but it's most probably benign. So 1 and 2, essentially 0% chance of the patient having cancer. 3 means probably benign, so there is some risk, and the data shows that up to 2% of the patients with BI-RADS 3 have actually cancer. So we treat this 1 to 3 as 0 for us, yeah? 0, no risk. 4 is a bit different. It's suspicious, and usually patient is advised to do a biopsy if it's virus 4. There are different classifications within virus 4, and the incidence rate of cancer can vary quite a lot. So in the cases where the patient was assigned virus 4 but didn't follow up with a biopsy, we discard these patients from the study because we cannot be sure whether there was a cancer or not. And bioreting 5 and 6 is definitely cancer, so this is the true cases for us. So during this 10-minute waiting time, we also collect some more data from the patient, like the age, the status of menstrual cycle, whether they have a pain, or whether there is a palpable mass on the breast, and whether there is any family history of breast cancer. Among these data, the palpable mass is the most descriptive, and in our data set, more than 60% of patients with palpable mass were diagnosed with cancer. So palpable mass usually means it's already, I mean, let's say it's not early stage cancer, yeah? That the cancer has already palpated. Besides this data, we also have a web dashboard that we use for storing the data and to visualize, but we also have a annotation tool for the doctor, where the doctor looks into the mammogram images and then annotates the approximate tumor locations. This is important for us to know where on the breast the tumor is, so that we can then use this information for our methods. So the prediction pipeline, it's quite involved. I will not go into all the details, but so basically first we have these 3 pictures, the frontal, left and right. It's a chest scan, so we need to first segment the breast regions out of this. Then once the breast regions are segmented, we go on with detecting abnormal regions, yeah? So these are the regions that are relatively like hotter compared to their surrounding tissues. Once we have the abnormal regions, we engineer features describing these abnormal regions. Then we have a step where we do anomaly detection on these features, and then we rank these abnormal regions. And then we basically take so the abnormal region with the highest anomaly score as the abnormal region of the breast, and then we use these features and then we aggregate these features with patient level or breast level other features, and then the final model comes in. So for the breast segmentation, we use now standard UNet architecture. We manually annotated around 6,000 images for the model, and on the test set the accuracy is above 92%. The metric used is intersection over union, and in practice we have seen that it's actually more than enough. I mean, we very rarely have cases where the annotation, I mean, the segmentation is really off, yeah? So there can be some small distortions here and there, but in practice it wasn't harming, so we basically paused developing on this segmentation model because it was good enough already. For the abnormal region detection, any segmentation model can be used, basically, but we use the region growing segmentation. So how it works, in few words, we basically binarize the breast region. So we use 32 bins. So say the temperature difference is 3.2 Celsius, then there will be basically every region will be 0.1 temperature off. Then we select the hottest regions, and then we start growing these regions until certain criteria are hit. And then we can also merge some regions depending how close they are together. This is basically the result for the abnormal region detection. As you can see here, actually, the tumor is on the right breast. The contours are a bit brighter for the tumor regions. And on the contralateral breast, you can see that there are still some abnormal regions. So we have to have a way of classifying which abnormal region is actually cancerous. So for this, we build some features. There are two types of features, basically, temperature-based. For example, the maximum temperature of the abnormal region, the mean temperature, the relative temperature of the abnormal region compared to the rest of the breast, or the relative temperature compared to the corresponding region on the contralateral breast. So we do a mapping of the region on the other breast, and then we compare the temperatures of the regions. And also, it's thought that tumor regions are generally more irregular than the healthy regions. For these, we have some features that describe these irregularities, like how much it deviates from ellipse, circle, or we use the fractal dimensionality, and other different irregularity measures as well. Once we have these features, we basically need, for every breast and every view, we need to aggregate these features. So in some literature, people basically use like the maximum of some feature or the minimum, or depending what the feature describes, but this is a bit unnatural. So we wanted to have a way of selecting some region which is the most abnormal compared to the other. So for this, we separated some subset of healthy patients and trained an anomaly detector on the regions of healthy patients, and then run this anomaly detector for the rest and get an anomaly score. And then we selected the abnormal region with the highest anomaly score. And in 90% of the cases, this is the region that the doctor annotated as the tumor. So for the ranking and for selecting the correct tumor region on the tumor's breast, this works. And then for the final feature set, we for every view, for every breast, we take this feature, it's all the features of this region, and then we also have features describing the asymmetry of the breast, like temperature asymmetry, how the median temperature difference is. We also have separated the breast into quarters and then compared the temperature differences for these quarters. And we also use the mean anomaly score for the breast and the area ratios of all the abnormal regions on both breasts. And then finally, we train a random forest classifier using a fourfold cross validation. And then we take the mean of the predictions as our prediction score. On the cross-validation set, the mean F2 score was 0.46 with a standard deviation of 0.12. And then finally, we took from December 2022 to April 2023, we conducted clinical validation in the same center where we collected the data. We scanned 431 patients, out of which 41 had a cancer. And the F2 score on the clinical validation set was a bit larger than for our internal validation. It was 0.51. So at least we know that the results generalize quite well. So what are the columns? In the first column are the results of thermal-only predictions, so where we only use these thermal images. On the most right is where we basically predict if the patient has a palpable mass, we say it's a cancer. If not, then not. And so 73% of all the patients who had cancer had a palpable mass, so sensitivity would be 73. The sensitivity of our thermal model is 58, but combined the sensitivity is 90%. So there is some complementary information, and we detect some cancers for the patients who didn't have a palpable mass. Yeah? So these are the confusion matrices. With thermal only, we detected 24 out of 41 cancer cases. And when we combine this with the palpable mass information, it's 37 out of 41. So we only miss 4 cancer cases. And the sensitivity using the thermal only model for the patients who didn't have a palpable mass was 64% compared to the patients who had the palpable mass. So it means that if we assume that the ones that didn't have a palpable mass were the asymptomatic patients, so the model accuracy on the symptomatic and asymptomatic is roughly the same, yeah? Even a bit better for the asymptomatic. We compare the model accuracy depending on the tumor sizes. So we have 2 groups. Below, where the tumor is below 2 centimeters and above 2 centimeters. The model works better, of course, when the tumor size is big, but the relative contribution from thermal is actually larger for the early stage cancers, yeah? Because there also they didn't already palpate. So so for palpable mass, it's 43. Our model is also 43. Combined is 71. Then the tumor types. We basically have the first column is where we don't have a biopsy result, so we don't have the type. The rest 4 are luminal A, luminal B, and then luminal HER2 and triple negative. These are types of cancers. So basically, from left to right, the incidence rate of the cancer types is going down. So the most common is luminal A, the least common is triple negative, but the aggressiveness of the tumor goes up. So the most aggressive is triple negative, the least aggressive is luminal A. Yeah? So for the most the 2 most aggressive types, with the medical symptoms, we detect all the cancer cases. But also for luminal A, the contribution is quite large with thermal and with symptoms. And finally, the age groups. So we have 2 age groups, below 50 and above. The model doesn't do that great for younger patients, and we think we know why this is the case and working to improve this. But again, the relative contributions are kind of the same for both age groups. So in terms of future work, as you remember, I said that there is this process of angiogenesis, of the development of new vessels. And we think that if we detect the vessels on the breast regions and incorporate this information in the model, we can improve the results. We tried different methods. The best works is this one, diffusion detector, which was actually originally proposed for detecting vessels on the human face for some face recognition applications. But we tried on our data set. It kind of works quite well. You can see the skeleton of the detected vessels on the right image. In terms of protocol, we are planning to extend our data collection in Armenia to new sites. And now we can do some more tests on the protocol. For example, we have seen that the younger patients usually are warmer compared to the elder patients, and maybe they need more time to come to a thermal equilibrium with the environment. And we think to extend this waiting period for younger patients from 10 to 15 minutes to have this effect. But also we are planning to build a thermal shield behind the patient and around the patient so that we minimize the environmental interferences when we are taking the thermal images. And then we are planning to do a multi-site clinical trial in Armenia. And we are in contact with our partners in India and Singapore to do some data collection there as well. Yeah, and this brings me to my conclusion. Thermal imaging seems to be a promising modality for breast cancer pre-screening. Combined with medical symptoms, it achieves high sensitivity, which is in line with FDA approval as an adjunct screening tool, and has a potential to detect the cancer at early stages. Thank you.
Having in mind that 80% of UK patients have detected the breast cancer between going to doctor's screening, it's a bit more reliable to, for example, to create an AI-based, for example, ultra-sensitive wearable patches on the breast to detect on 24/7 mode the creation of this cancer, all these differences, for example, thermal shape differences in the cancer growth, and to make it more efficient cure. For example, that they could be thermal or shape-based or having both features simultaneously. What do you think about it?
Yeah, sure. I mean, this is what adjunct tool means. Yeah, so you can use like mammography results, the thermal technology or medical examination, and combine all these results together. But so that we don't have a confusion, this 80% refers to these 6,000 interval cancers. I'm not saying that 80% of UK cancers are because of interval cancers. Yeah, just to be clear.
I was kind of expecting that there would be some kind of convolution on your network. So have you tried this, or?
Yeah, sure. I mean, of course, the first thing you try is convolutional network before going all these abnormal region, anomaly detection, feature engineering. It didn't work. Yeah, I mean, probably the data is not that much for the moment. I think last year or beginning of this year, Facebook announced its segment anything model, and they even have a thermal modality there. So we even try to embed our images with this model and then see whether this gives some boost to our models, but this also didn't work.
It's for segmentation only, or just using as a...
Well, it's we wanted to extract features from these embeddings. So this was the idea, because for the segmentation, I think it works quite well. And the way we segment the abnormal regions, actually, we also infer some new features. I didn't talk about this, but for example, for how long, how many spans the region grows, this is also informative. Yeah, I mean, you have a hot region, like for how many spans it grows. So we extract some more features. So I don't think we will need to do the segmentation with the model, but we wanted to extract some new features with these embeddings.
So maybe one question. Yeah. So this the rating, the standard rating from 1 to 0.
Yeah, pirates.
That's done when the nodule is discovered, correct? Or is that
the pirates?
Yeah.
No, I mean, so you go to mammography, and then you get a result, which is one of these numbers from 0 to 6. So 1 and 2 means you don't need to worry, just go home.
Is there a nodule there or no?
So 1 means there is nothing. 2, they found some nodule, but it's I mean, 99% is benign. 3 means you better come in 6 months because I'm not sure. It can be both. 4 means it's probably suspicious, so maybe do a biopsy. 5 means like 97% cancer.
What do you think is the reason that neural networks do not properly work here? Is like the limitation of the data? You think it's impossible to squeeze more, or just we didn't found yet the right? Like, what do you see? Like, does it overfit?
It overfits very rapidly. So we tried to do some data augmentation to avoid this, but it didn't help. Also, the class imbalance is quite high. So I'm optimistic that at some point the neural networks will work. It's just a matter of having more data, I think.
More data.
Yeah.
Because you know, I understand that it's extremely hard to get ground truth for this. I mean, you get it through other analysis, right? It's not that there are experts who can just look at the thermal image and give you. So you do not have this baseline to compare.
No, actually, we tried for our doctor to just look at the thermal and predict. Now we are doing better than him. So, yeah.
So probably there is not much signal. Yeah.
Yeah, I mean the differences between malignant and benign tumor is very small, so it can be a couple of degrees from here and there. So probably this also, I mean, maybe if we pre-process the images in a more clever way, maybe we can aid. For example, the abnormal regions that we detect, maybe we can highlight them in somehow on the images. Maybe we need to do something like this to aid.
That's also feature engineering.
Yeah, sure. Yeah. Just give the image, predict, yeah.
Thanks for the talk. Probably a technical question. You told that you use the random forest. For any only tabular data which I analyze to make a classification, I would probably as a default go to LABZ.ai or whatever. I mean, you already kind of overfit all the training data with the random forest? Or what's the reason why you don't go?
Yeah, I mean, we couldn't make LABZ.ai not to overfit, basically. It was hard to, and there are so many hyperparameters there. And also LABZ.ai, I think, works best, I mean, better when the data is big enough. For small data, I would probably still go with random forest.
I'm sorry, what were the most important features?
So the most important features were the temperature-based features, especially the one where we compare the relative temperatures mapped on the contralateral breast. So basically, it means how much hotter this region compared to the same region on the other breast. This was the most important. Actually, in previous literature, these shape-based features were thought to be important, but we didn't see this. I mean, it could be also because they use some more advanced cameras. We only use the smartphone camera. So it could be that if the camera, the thermal resolution is high enough, maybe you see more structure. But for us, these shape-based features were not that important.
Did you go through a feature selection process? Is there some other features that you thought would work?
Sure. I mean, we even tried some Fourier features, like Fourier transform the image because this is natural. It's after all, it's a thermal data, but we couldn't make it work.
Like when you think about the complexity of tasks itself from machine learning and like application of these, like as I understand, this will be used for like maybe future response with help camera and people that do more screening. So maybe like if you think about making the task more easier for machine learning in terms of like not detecting malignant or not, but just detecting that you should pay attention or just always go through.
Yeah, sure. I mean, it depends on the market basically where you want to use. For example, for a countryside where people don't go to screening anyway, I mean, any percentage of sensitivity is better because you compare to nothing basically. So you can lower your threshold and then In our results, yes, it's 60% sensitivity and 90% specificity. What this means? It means that if you scan 15% of your population, you will find 60% of the cancers. So this is better than not doing any scans or randomly selecting 15% of the population and then do the mammographs. Yeah? So it really depends. If you go to developing countries, then you need very high sensitivity and very high specificity. But for other markets where people don't do the screenings anyway, any solution is good enough. And this takes like 20 minutes and a phone.
Okay, let's thank the speaker
Yeah,
again.
thank you.